Okay, so morning, everybody. Today we will be discussing electric potential. We have already reviewed some quick facts from intro physics in the previous class, and today we'll continue to discuss this topic. So from Maxwell equations, we know that the divergence of E is rho, the charge density, over epsilon naught. Now, how about the curl of E? What is the curl? So the del cross into E field for electrostatic fields. Do we know that? That is 0, yes. Thank you, Kenneth. The curl of E is 0 for electrostatic fields. We can take a look at a point charge as an example, okay? So for example, I'm showing you the electric field for a point charge. You're already very familiar with this format, right? This kq over r squared, 1 over the inverse r squared law. 1 over 4 pi epsilon naught is simply just the the Coulomb constant. So because of math, if you turn to your textbook, just take a look at the flyleaf. It shows you how to do the curl in spherical coordinates. And this is just any vector, any random vector. So the curl of any vector would be, for the r hat, you will take the phi hat component of this vector, you'll plug in the theta hat component like so, and likewise you do the theta hat and phi hat, things like this, right? So if you do this quickly, you can eyeball this and let's see if it is indeed curl of E is 0. The E only has a R component, which means it does not have a phi component, theta component. So everything here is 0, right? It only has an R component. The R component is 1 over r squared, but it does not depend on phi, does not depend on theta. So because it doesn't have these dependents, you can see all of them is 0. And you can quickly get del dot E is 0. This is for calculating it in the spherical coordinates. You can do it in the in Cartesian, not as easy, but you can do it. So I'm wondering, I'm just going to ask, let's say, suppose you're trying to do it in the Cartesian, okay? You're going to say, okay, E sub r is constant r squared, r hat. In Cartesian, you want to rewrite everything in terms of x and y. So I'm going to do something like this. I want to ask you if you think that is correct. Z squared, sorry. And x hat plus y hat plus z hat. So is this correct? Which means if I do dE dx, I'm just going to take this and take the derivative. Is this do you think this is correct? What do you think? Okay, some said yes, it is correct. Other thoughts? You could eyeball this. If you do that derivative with respect to x and y and z, you can see quickly it's not going to give you 0. But we know that the curl of E for this point charge is 0. From this step to this step, there's no problem. From here to here, so let me ask you this question. Do you think r hat is x hat plus y hat plus z hat? Is that correct?
No.
Okay, so instead, how do we write x r hat?
We write it as the magnitude of r times the r directional vector, correct? Or divided by, yeah, divided by it.
Okay, all right, very good. Is Hunter, was that Hunter?
Yes.
Okay, so let's further rewrite this. So R is x hat, y hat, z hat, and R magnitude is this. So you can see that R hat is not x hat plus y hat plus z hat, but instead is x over this entire thing, x hat, and y over this entire thing, y hat, and z over this, z hat. Okay, if you do write this and plug it in, you're gonna get curl of E will not be 0, and now that will be wrong. So this is wrong. Okay, so if you're curious to do this in the Cartesian, you just make sure that you write your R hat correctly, and then plugged in, you can do it as an exercise to make sure that the curl of E is also 0, just like what you got in the spherical coordinates. Okay. So the curl of E is 0. Now, if you have many E fields, simply just, this is a superposition of many of the E field. And that is curl of each individual of them. And each one of them is also 0 because they're all static fields, right? It's still 0. So curl of E for static fields is always 0. Okay, so let's look at in this class, we will need to borrow a lot of math. So we'll start with 2 of them. The first theorem is for any function, a random scalar function, then the curl of the gradient is always 0. So this is what we know from math. The curl of the gradient of any function is 0, no matter what kind of function it is. Okay, so what is the use of this particular math theorem is that because in physics, we know that electrostatic field has no curl. That means we can always write this E by representing it using some gradient of some scalar. So this math theorem tells us E can always be represented using some kind of scalar function. And that is the electric potential in this case, a scalar potential. A lot of times we call it scalar potential because the potential is a scalar. Okay, so that is why we can write E using the gradient of potential V. So it's from that particular math theorem. And now in terms of, okay, if we know how to write E, how do we represent potential? Now we can use this second math theorem is, this is a practice in your week 2 recitation, is also a problem from your textbook. The gradient of 1 of curly R is negative 1 of R squared R hat. So that can be done with a quick derivation. So here, let me go ahead and present you with this clicker question. From this clicker question, we will be able to find out how do you represent the potential V. Okay, so let's look at this. This is a generic format for calculating E field giving a charge distribution. Okay, you have your curly R here, you have your volume integral here, you have your square, R squared here. Now is R minus R hat in Cartesian. So this is a generic formula. It's also true, the gradient of this is this. This is just the math theorem I just showed you. And what is gradient? Gradient is taking the derivative in X and Y, Z direction. So the question is it okay if I take the delta sign, put it outside of the integral? So you can see from this step to this step, you simply take the delta out of the integral. Is this mathematically correct? So that is the question. I'll let you take a screenshot and in the breakout rooms for discussion for about 1.5 minutes, and I'll bring everybody back, okay? Okay, any last minute vote? Okay. If no vote, I'm gonna go ahead and close this. Let's take a look at your results. Okay, majority of us voted for no, it's not okay. So can anybody tell us what is the reason for you think that operation is not okay? By taking the gradient in front of the integral.
Before you take it out, it's operating on 1 over big R magnitude, and afterwards it's also working on the rho of R.
Okay, I see. So you're also operating it not just on the 1 of R, but on the rho of R. Okay, so that's why it's not okay. Someone also said integrating said 1 of R is different from integrating 1 of R squared. This one, they haven't really done 1 of R squared. This is still 1 of R in these two expressions. So so you guys think by putting the differential sign also on rho is not okay. I would agree with you that we have to be very careful in manipulating our integrals. However, let's think about the variable dependence. Rho is a charge density and it depends on the source, right? So rho is a function of R prime. So rho can be function of X prime, Y prime, and Z prime. Okay, and what about this gradient? You are taking derivative with respect to the field, right? You're taking derivative with respect to X and Y and Z. And does delta depend on your source variables? It's only depend on your field. It doesn't depend on your prime variables. So you actually can take it out of the integral because it's not going to do anything to your rho or d tau. And delta is not a function on prime ones, okay? So it's okay, you can take it out. It's not going to affect the prime variables. I know it looks kind of weird, but it is indeed true. So this mathematical manipulation with your good intuition, normally it would not be okay. We got to be very careful. But in this case, it's actually fine. So yes, we can take it out, which means E can now be represented using gradient of this entire thing. And we just previously said E can be represented using the gradient of the potential. So potential is this entire thing, is this thing. Okay, so potential V is 1 over 4 pi epsilon naught, the volume integral of your charge density divided by the separation distance, R, curly R, magnitude. And you can see it is a scalar, right? Unlike E, which is a vector, we go back here, it has a vector sign. Your V is a scalar. Now, we add a potential constant because you can take the gradient. For example, you take d dx over 2x, you get 2. But you get d dx over 2x plus 3 is also 2, right? Or 2x plus 5 is also 2. You can see you can get infinite number of the potential. That will give you the same electric field. So there's going to be a constant. There are all kinds of constants that can satisfy this. So a lot of times we need to define a reference point for your potential. And it's all relative. Where you define your potential as your reference is really relative. Just like in intro physics, we define our reference point for gravitational potential energy to be 0. A lot of times we define the ground to be 0, but you can see that's not unique. You can define your table, or you define somewhere underneath the ground, as long as you keep it consistent with your potential choice. So yes, this is our expression for V, giving some unit, giving some kind of a volume charge distribution. That's your potential. Okay. Just to recall, E for point charges is KQ over R squared, right? R hat. V for point charge is KQ over R, just scalar. So sometimes if you do forget how this integral look like, you can remind yourself from intro physics, sort of the generic expression, and then write it out, fill in the details. It might be a little bit easier. Now, at this point, let me introduce a third math piece. Stokes theorem, that's something we already know. Okay. So please remind us, anybody would like to remind us, what is Stokes theorem?
Is a line into, what is it? A closed line integral of some vector field multiplied by some vector line element, and that's equal to a
Okay.
closed surface integral
Okay,
of the curl of that field.
excellent. Thank you, Hunter. So a curl of that field on a surface integration is equal to the line integral of the boundary of the surface. So because the this side, the surface is defined by the closed boundary, the surface integral is actually open. It has to be open. It's a divergent theorem. The closed surface give you a volume, right? So a closed line, you close a line, right? That define an open surface. So any closed line define a open surface. So this side has to be open. The other side has to be closed. Very good. That is our Stokes theorem. So we use that to help us think about what it means to have a curl of E is 0. In this case, because the curl of E is
Dr.
always,
Moran,
I'm sorry, yes?
may I ask you again what the difference was between an open and closed surface? Does a closed surface represent path independence?
A closed surface, take a piece of paper, it's open. If you want to close it, you have to wrap it around and close the top and bottom. It's like, okay, a balloon is a closed surface, but if you cut it open, then that's an open surface.
Right. Okay. Yeah. Okay. I see what you're saying. Thank you.
Right. Or maybe this is not, I don't know if it's like a ravioli, like if you have a dough, a piece of wrap, before you put stuff filling in it and close it up, it's open, right? You can
Right.
put some make it into a dumpling, it's closed. Okay, so what does it mean for a curl E is 0? If curl E is 0, that is equivalent of saying E dot into DL is 0. Okay, so so the curl of something is describing all space. You can see that my field is in all space, in all region, in this entire region. So it's describing, okay, what is happening at each of the individual point. So it's kind of like a swirl at each point. When you put a paddle wheel in it, it's going to rotate. So the curl, however, the circulation, this is at the boundary, right? This is only at the boundary. So this is looking at the circulation, the line integral around the boundary. So for example, you can imagine if I have a lot of curl inside at each individual location. Here I have a curl here. I have a curl here. Everywhere within this region, then that is equivalent of computing. I'm sorry, my arrow not consistent. Okay. All right. So it's equivalent of looking at simply just what is on the outside. Add everything up, it's equivalent of looking at, okay, there is sort of a non-zero circulation from the outside. This is equivalent of looking at what is the line integral around the boundary of this? Okay, so these two give you the same kind of information. So if curl is 0, then the line integral is also 0. They say it's the same thing. Now, I wanted to make an analogy. For example, let's say the fish wish to evaluate the curl of the field that it's in. So what the fish would do is to do a line integral around the boundary, swims around, and the fish compute this line integral and get, okay, this line integral of some random field is not 0, which means there must be a non-zero curl inside this boundary, inside this area, non-zero curl. So what would the fish conclude? Where do you think the fish might be in?
In a whirlpool.
In a whirlpool, yes. Very unlucky is actually in the toilet bowl. That's not really good for the fish. So it's just kind of an example to show the relationship of your curl and the line integration. Line integration is a circulation around the boundary. Now, this is really cool because we know that the curl of E is always 0 for electrostatic field. Then you can see the line integration is always 0, and that tells you this field is path independent. Now we also said E is a gradient of V, right? Now, which means when you look at V, this integration of E dot into dl, this is what we discussed. So if this is closed, it is always 0, which means if you look at the beginning of a point and the final point, if you're looking at the same point, there must be no electric potential, which makes sense, right? If you looking at this point in space and you do a closed integration and you go back to the point, there must be no potential difference. So V of these 2 points must be 0. So this is only V is only dependent on which point you have in space and regardless of what path you take. So you can, for example, point A and B, right? You can do a straight path or you can do a curved path. Then VA minus VB only depends on the potential A and B. Only depends on the potential at these 2 points, but does not depend on path, which means it's path independent. Okay, whatever path you take doesn't matter. This one more math function is a fundamental theorem of calculus. This is, we kind of got through this already, but if you want to see it a little bit more clear, how do I change E equals curl V into the integral format? You can think about this math. This piece of math is, you can see this is just the differential, right? Derivative with respect to function, but you integrate it over, you get the function itself. So at just a function at the boundary. So likewise, if we're looking at the curl of V dl is going to be VB minus VA in this case, right? So this is the potential. So that's why E dl negative is VB minus VA. Okay, so this is telling you the potential difference between 2 points. So you can think of it's the initial minus final, because we always use the final point minus the initial point. So from point A to B, the difference is negative integration from A to B E dl. So this is where it comes from. How do you get this to become this? In between that, we have borrowed a piece of math fundamental theorem of calculus to get this. Or it may look so obvious to you, actually it is obvious. You may not want to think about this at all, that's fine. Okay, so we have discussed that the potential difference can be calculated by integrating your E dot into dl, and this is path independent. As long as you have those 2 points in space settled, you have a fixed potential difference. Which also means now if there's no electric field in between, if E is 0, then there must be no potential difference between two points because your integration is 0. So here, let me present you with this question that is on your pre-flight that you have already done, I believe last Wednesday. The follow-up question has to do with a lot of your pre-flight questions, but before we go review the questions you answered, let's first answer this particular question. So I'm giving you a spherical shell with uniform surface charge distribution, sigma. What can you say about the potential inside the sphere? And we define our reference point to be infinity. That is, as a reference point, potential is 0, okay? So take a screenshot again. You can have your discussion for about 1 or 2 minutes. Okay, a few more seconds for everybody to wrap up their voting. Okay, any last minute vote? Seems like I get most of the everyone. Okay, I'm going to go ahead and close this. Here is our results. Seems like we all agree it's either it's a constant, whether that constant could be 0 or not 0. There's some options for choices for E has to be a function with respect to position. Okay, well, let's discuss this together. Before we do the E, first of all, let's figure out if we can answer the question about the E field inside. What do you think the E field inside this sphere? Is it a function? Is it a 0? Or is it some constant, non-zero constant?
I still think it's a function.
Okay, can we compute this function?
Yeah, we can.
Okay, how do we do that?
So let's say we take some point within this shell, right? And
Yes.
we write I would write an R prime vector
Okay,
from one charge on that sphere to that point, and then I would write another
okay,
vector, call it R, from the center to that point,
okay.
and then I would, well, you could use Gauss's law also. You could use it on the inside.
Okay, all right, let's use Gauss's law. First of all, we have a shell, which means we do have spherical symmetry. So that if E inside is not 0, it must be pointing in the radial direction because we have the spherical symmetry. That means if we do use Gauss's law, we're going to draw the spherical Gaussian surface like here. And then we're going to do, okay, use Gauss's law. EDA is Q enclosed over epsilon naught.
Oh, it's not.
Okay, not a function, you mean?
So it isn't a function. Okay.
Okay, so it's gonna be E 4 pi r squared. Q enclosed, now you can see we don't enclose anything, right? We don't enclose anything. Your charge is outside of this Gaussian surface, so it's 0. Now E has to be 0 inside. Okay, very good. Okay, so now we have established E is 0 inside. What does that tell us about the V?
There's no voltage on the inside.
So if E is 0, let's see how we get voltage. And which means, okay, E is the gradient of V. E is 0, meaning that whatever voltage is, when we take the gradient or derivative,
Oh,
has
it's a constant.
okay, so it can be a constant, yes. This constant, so the question is it a 0 constant or a non-zero constant? Or is it could be A or B? There's an option there too. Let's see the chat. Dell, thank you for your comment about using Gauss's law. So what do you think about this constant? Is V a 0 constant or non-zero constant, or could it be either? I want to point your attention to, with this particular reference choice, can we have V0 inside? Given V infinity is 0. Can V inside be also 0? Okay, no, and why is not? Why not? So let me ask you this question. E is infinity, now the E field outside of the sphere, I imagine it would be radially outward like that. So in the direction of your electric field, the potential decrease, right? Because your E field pointing from high potential to low potential. Okay, so here from the surface to infinity, going all the way to infinity, you get a zero potential right here, zero. So as you go toward where your charge is, your potential has to change, it must increase. It's like the water flowing from higher pressure to lower pressure or higher place to a lower place. So here you're dealing with on the surface, you must be dealing with a non-zero V. Do you agree? It cannot also be zero. If it's zero, then your E field should not be pointing from 0 to 0. There shouldn't be any flow, right? There shouldn't be any electric field if there's no potential difference. So I can be sure that the E field, the potential here on the surface must be non-zero. And in fact, it must be a larger than zero constant. I'm sorry, the potential, not E field. V at the surface is non-zero. So what about E here in the center? From the center to the surface, is there any potential difference? From any point in the center, if we do a line integration from here to here, we are integrating over E, right? This is my surface charge. E is 0 inside, which means if I'm looking at any point A in between here and B, from A to B, E dl, because E 0 inside, anywhere inside from A to B, so this is 0, which means VA minus VB, the potential difference between them is 0, right? There must be no potential difference from here to here. Now, if I establish the potential here is non-zero constant, the potential inside is the same non-zero constant. It's also, this is the equipotential. Your potential anywhere inside is the same as your potential on the surface. So it must be a non-zero constant everywhere inside. I'm not getting any responses, so I'm just want to ask any questions that you have about this particular question, because I want to make sure you understand this before we move on to answer the pre-flight questions. Anybody want to ask a question?
I don't really have a question, but my mind isn't fully there yet. Do you think you can just explain it again, please?
Okay, so let's see where you, okay, so take a step back. Do you agree that the potential on the surface is non-zero?
Yes.
Okay, we know that because from here to infinity, E is pointing to infinity. So as you go, your equipotential lines, right, it has to increase. So this must be some non-zero constant. Let me just call it, let's say potential here is 10 volts. I'm just gonna give a random number, 10 volts. So if we agree this is 10 volts, my next step is I argue anywhere inside the sphere is also 10 volts. Anywhere. The reason is that because E is still 0, the potential difference between any points in between has to be 0. And the potential from here to the surface, you're still dealing with, you know, an area where E is 0. There's no change. If it's not 10 volts, you must have an electric field, right? If I say E here is 9 volts and here is 10 volts, you must have an E field. Anything other than 10 volts, 11 volts, you must have an E field. But there's no E field. Okay, thank you, Nicholas, for asking this question. I'm sure others have appreciated that as well. Okay, so we have established V is non-zero constant everywhere inside, and it's larger than zero constant. Let's look at your pre-flight questions.
I also wanted to make the note. If you go back to that integral that we defined for the voltage, not that one, the one that we defined before, where we have the charge density.
Oh, okay, so all the way above
Yeah.
here, no, sorry, here.
Yeah, one way that I thought about it was that because there's no electric field inside of the shell,
Mhm,
the charge density would be equal to 0.
mhm.
So if you replace the charge density, which is equal to 0, that integral will go away and you just be left with a non-zero constant.
Yeah, you can also, let me think. Yeah, within the inside, there's no charge density. You're right, and the integration of the part that with the charge density arises of potential, that part is 0 indeed. Yes, that's also a very good way to think about this. Thank you, Hunter. Okay, so go back to our pre-flight. Now the question is, can we instead choose a different reference point? Instead of using V infinity equals 0, can we make V at the surface to be 0? Is this choice okay? You have done this, so I'm wondering, what did you choose? Or maybe you have a different thought now?
I'm hesitant, but I'm gonna say yeah, as long as you stay constant with it.
Yeah, so if there is a fixed potential difference between R's of R to R to infinity, let's say if from R to infinity is some fixed potential difference, which there is. There used to be 10 volts here, 0 volts here. If this is 0 now, you just need to make infinity to be negative, and that's still okay. You're right. That is still a valid choice. Yeah, so yes, Brendan, the infinity now is going to be a negative constant. Yes, so it's okay. So what would be the sign for the potential at the surface and the potential in the center? We kind of already answered this. What is the sign of this?
It would be negative. Would it?
So this is a
It
potential.
would be 0.
Yes, because everywhere inside is the same 10 volts, right? Anywhere 10 volts, so 0. Where in space is a divergence of E non-zero? What is the divergence of E? Divergence of E is charge density over epsilon naught. So where in space is divergence non-zero?
Would it be past the surface?
Yeah, exactly. That's on the surface. So where is density non-zero? Density is non-zero where the charge is, and the charge is living on the surface. So only on the surface you will have a non-zero divergence. And where in space does the curl of E vanish? Curl of E is always 0, right? Always. So where does it vanish? It has to be everywhere in this case. So you will actually choose everything because it has to obey the no curl rule for the electrostatic field. So where in space, and all of them, you actually choose everything, choose all that apply. Okay. All right, so hopefully after this, we understand the relationship between V and E, and you must be surprised how little can we tell if they just simply tell you about a voltage at any given point. What's important and what's meaningful is the voltage difference between 2 points, because voltage is so relative. Without defining a reference point, knowing the voltage about one particular point in space is not very useful. And so let's take a look at this question. The voltage is 0 at a point in space. What can you conclude about the E field? So I'll let you vote here. You don't have to go to discussion. Okay, I got 31 out of 33 votes coming in already. Any last minute vote before we take a look? Okay, any last minute vote? Okay, let's take a look. Here is our results. E is 0 is choice A, is non-zero is B. You cannot conclude anything about E is choice C. The kind of majority chose A, that E is 0. Okay, so notice that, yes, because E is a gradient of V, I think a lot of you saying if V is 0, then E is 0. So I would like to make an analogy of, let's say V is equal to A. Well, how should I do this? Gonna draw something like this. Let's say we are dealing with a function of f of x versus x, okay? Oh, sorry, no. F of x versus x is fine. Okay, at some point, f of x is 0. But if we're looking at the derivative, now if this is a position time graph, then the derivative of this is a slope, right? That is your velocity on your position time graph. So you can see that even though the function here has 0, the slope is non-zero. So just because v is 0, gradient is taking the slope, right? It could be non-zero. So E field is not necessarily 0 at that point. We cannot really say it's not 0, but it's not for sure it can be 0. So to conclude, we cannot really tell anything about the E field. Giving us a potential at one given point is pretty useless. You got to tell people what your reference is or what your potential difference is before you can draw more information about the E field. So the correct answer is C. Okay. So this is a quick summary of what we talked about. This is just the page for you to look over. We still have a couple questions coming up. I got a message. I don't know if I already answered the question. Someone asked for non-zero divergence of E. Would it be on the surface? or outside of the surface or just on the surface. So for non-zero divergence E for the pre-flight, it will be just on the surface because your charge only lives on the surface. Your charge density is non-zero only on the surface. So outside, inside, zero divergence. Okay, so a lot of times we find potential first because it's easier. You find the potential, it's a scalar, so it's easier to find a scalar. And you take a derivative, you can find your E field. So first, let's do a quick question on this one. It should be quick. And then we will solve a problem together, finding the potential first, and then find the electric field using the potential. So, okay, if we have a uniform charged terrain on the XY plane, and we define the infinity as zero potential, what would be the voltage on Z, at Z on the Z axis? Okay. So you can see the electric field is actually quite difficult to compute, but the voltage in the center is quite simple or straightforward to compute. Okay, so I'll let you vote on this one. No discussion needed. Again, we remind ourselves V is K dq over script R separation. So if you want to be reminded where script R is, you can take a look at this page. This is your little chunk of dq, and from your source to your field, that's your R. Okay, so V is again dq over R. So if that helps answering this question. Okay, 10 more seconds for everybody to finish their voting. Okay, all right. So I want to see yes, the majority of the answer C is correct. Very good. The distance you can see at any point on the source, right? They all have the same distance, separation distance from your source to your point of interest, right? If you look at this, this is Z, this is A, this is 90 degrees. So R is square root of A squared plus R Z squared, right? The overall of the dq becomes capital Q. So C is correct. You can see doing the potential is very easy. If you want to E from the potential, you simply take derivative. You can get your E field. If you want the EZ, now you take the derivative with respect to the Z. So now let's look at an example. Well, this is a sort of a triangle showing you the relationship between density, electric field, and potential. Okay, from one, how do you get another? So this is a sort of a relationship. Quickly summarize some of these equations we have seen. Okay, so now for the rest of the time, let's work on this example. Let's say we have a uniform charge distribution from negative L to L, lambda, a finite line distribution. Okay, in this case, it's on the z-axis, and x is pointing to the right. So y is not shown here, but y is pointing into the page. That's why. So a random place point in space is located at x, y equals 0, z. So we want to find out the potential at a given point. Okay, so V, let's do it together. It's a little bit charge distribution. Okay, and this little charge has a variable z prime. Okay, and this is r, script r. Okay, so r is x0z, r prime is 0z prime. So script r is r minus r prime, which is x0z minus z prime. Okay, potential V is 1/4 pi epsilon from lambda dz prime. Well, this is your dq, right? This is just the dq over r. R is x squared plus z minus z prime squared, square root of that. And z is from negative L. Z prime is from negative L to plus L. Okay, so that's it. You can see it's a straightforward setting up the integral. And then this integration, we need to use Mathematica. And it's a natural log of z prime. So I get lambda 4 pi epsilon naught L to negative L lambda over 4 pi epsilon naught natural log. So plug in the limits, L plus z z minus L so z plus L over z minus L, this is your V as a function of with respect to the z variable. Okay, we have done this. We have done the electric field given this distribution. We have calculated it previously. Now that was quite a long calculation, but now you got your V is not so long. To evaluate E for this field, for example, if you want to know what's the E field in the middle of the charge, then Z is 0. So if you want to know where right here in the middle, then you're looking at Z equals 0. So V in the middle becomes this. So E sub x dv dx is the only one that's non-zero. E sub y, so negative dv dy is 0. E sub z dv dz is 0. Okay, you can see this follows from my expression for E, for V. So E sub x is dv dx becomes lambda over 4 pi epsilon naught, so negative sign, negative 2L over x squared plus L squared. And that becomes 2 lambda L 4 pi epsilon naught x L squared plus x squared. Okay, so you can calculate your E field in the middle by getting your V expression first. It's in the x hat direction only, right? So in the middle, you can see the E should be pointing to the x direction only. You can verify this by doing direct integration for your E field. You can do direct integration and you should get the same result. Right? You should get this result. Okay. So you're in the textbook, you have an example, I believe at 2.2. This is the same except the charge was on the x hat direction. Here I put it on the z hat direction, but your result expression should be very similar. So you can go back and review that. Okay. All right, so turn to the summary. We have a definition of the potential between two ending points, and to uniquely define your potential at any given point, you have to define a reference point, right? So V reference is defined as 0. So usually we do infinity as 0, but it's not unique. How do you compute it? Given a charge distribution, you can find your V. In this case, I give you a lambda. We have do a line integration, we got our potential. What good does it do? Why do we care about potential? Now, sometimes to do the potential first and then derivative give us E. That's a little easier to compute than doing the E itself. And where does this come from? It comes from that the curl of E is always 0 for stacked field. And with the math, we know there must exist a scalar function for every E field. So E can be expressed using the gradient of a scalar function. And that also indicate your E integration around any closed loop is 0. This E field is path independent. Your potential is decided only by a given point in space. Your potential has also to be continuous, meaning that if you compute the potential for V r less than r, you take the limit to be at the boundary. So V inside at r equals r must equal to your V outside expression when your r equals r. So at any given point, E has to be continuous. You cannot have a sudden jump on your E field. So, and also you can always refer back to these slides, giving a row, do integration, giving to do the E. And the other way, that is something we're going to discuss more in detail later on, is the Laplacian of V is rho over epsilon naught. So we kind of already touched on that previously, right? Now, if you give a density, again, you do integration to get your E to be the other way around. The divergence of E is your charge density. Curl of E is always 0. Now, between V and E, one is the gradient, give you the E, the integral of E give you the potential. So you can have this relationship and try to be more familiar with all of these relationships. Okay, we kind of finished everything I wanted to discuss today. We can start and early. If you have any questions, feel free to ask me. But if not, I will see you guys on Wednesday.
Thank you, Dr. Ryan.
Thank you.
Thank you, Dr.
Yes, thank you, Dr. Ren.
Thank you. Bye, everybody.